There's a liquid that costs $2, comes from any pine tree, and makes wood harder than many grades of structural steel. Not slightly harder, not comparably hard. We are talking a 300% increase in surface hardness on standard softwood lumber, a treated plank that resists denting, cracking, warping, moisture penetration, insect damage, and fire permanently after a single afternoon of treatment. The Vikings used it on longships that survived decades in the North Atlantic. Egyptian craftsmen used it on wooden sarcophagi that are still intact after 3,000 years underground. Japanese temple builders used it on wooden structures still standing after 200 years of typhoon seasons and humid summers. And then the modern lumber industry opened its first pressure treating factory in 1938. And within 20 years, this knowledge had been methodically removed from every mainstream building guide and every contractor training program. Not because it failed, because it worked too well. And because a $2 jar of pine resin cannot be metered, cannot be patented, and cannot generate the $600 billion annual revenue. This is the story of pine resin wood hardening, the oldest building technology on Earth, and the secret that built empires, sailed oceans, and outlasted every synthetic alternative ever invented. Welcome to Fixvival. If this knowledge matters to you, subscribe and hit the bell. This is where we open the vaults that the industry sealed shut. Let me take you back 3,200 years to the eastern coast of the Mediterranean. The year is roughly 1200 BC. The Phoenicians are the greatest shipbuilders the ancient world has ever produced. Their merchant vessels cross open ocean for months at a time. They carry tin from Britain, purple dye from Tyre, and cedar from Lebanon. A Phoenician ship hull is not just shaped wood, it is transformed. Shipyard workers coat every plank in heated pine resin before assembly. They call it pisasphalt, the black gold of the shipyard. The result is a hull that lasts 30 to 40 years in salt water. Modern untreated wooden boats rot through in just 5 to 7 years. How did they discover it? The same way every ancient civilization discovered chemistry, by accident and then by careful observation. Resin seeps naturally from wounded pine trees. An ancient forest worker notices a fallen pine log soaked in its own resin does not rot. Other logs around it are black with mold. The resin-soaked log is still solid after 3 seasons. That observation travels. By 800 BC, Greek shipbuilders in Corinth are using heated pine resin, which they call colophonium, to treat warship hulls. The word survives today as colophony. The Rosen violin players apply to strings. Same molecule, different application, same 3,000-year history. Jump forward to 793 AD. The Vikings have just launched their first raid on Lindisfarne. Their longships are the most sophisticated watercraft. They are built from oak planks treated with pine tar. Viking pine tar is applied hot, penetrating 4 to 6 millimeters into the wood. The Vikings were not just waterproofing their wood. They were fundamentally changing its molecular structure. They just knew it worked. Meanwhile, in Japan, carpenters of the Nara period are developing urushi, lacquer derived from the sap of the toxicodendron tree. A natural resin penetrates wood grain, polymerizes in place, and creates a material harder and more moisture-resistant than the original timber, horyuji. Temple in Nara contains urushi-treated structures that have survived 1,300 years. Its surface hardness is equivalent to mild steel, now to 17th century Scandinavia. Norwegian and Swedish tar burners developed the most sophisticated pine resin processing system in the world. The Swedish tar company held a monopoly on exports. The Royal Navy of England was their largest customer. A single 74-gun ship of the line required 14 barrels of pine tar per year. The British Navy operated over 200 such ships. That is over 2,800 barrels of resin consumed per year. This was industrial-scale materials science, running continuously for over 2 centuries. It worked with a reliability that no synthetic alternative has equaled since. From ancient ships to modern science, the story of resin continues. Now let me explain exactly why this works. Because the science is as elegant as anything modern chemistry has produced. And it comes down to one process: polymerization in place. Wood is primarily composed of 3 materials: cellulose, hemicellulose, and lignin. Cellulose gives wood its structural tensile strength. Hemicellulose provides flexibility. Lignin is the natural glue that holds the cellular matrix together. The weakness of wood is in the spaces between these components, microscopic channels and pores that allow water and oxygen to penetrate and gradually break the cellular structure apart. That process is called rot, and every piece of untreated wood is engaged in it right now. Pine resin, chemically a mixture of abiotic acid and terpene compounds, is a liquid at high temperatures and a solid at room temperature. When heated and applied to raw wood, the resin flows by capillary action deep into the wood's pore structure. It does not sit on the surface like paint. It fills the cellular channels from the inside, then it cures. The terpene compounds undergo oxidative polymerization. They absorb oxygen and link together into long molecular chains. This process converts the liquid resin into a solid polymer network. The wood becomes a natural composite material. Standard untreated Scots pine has a Janka hardness of 1,150 newtons. After treatment, it reaches values between 3,200 and 4,100 newtons. That is approaching the range of structural aluminum alloys. The moisture resistance numbers are equally striking. Untreated pine absorbs 35% of its weight in water. Fully resin-treated pine absorbs less than 4%. Water cannot penetrate the polymer matrix. No water penetration means no freeze-thaw expansion, no mold, no rot. The treated wood's decay process is essentially halted. In 2009, researchers measured 800-year-old Norwegian stave church timbers. Treated sections had less than 12% degradation over 8 centuries. Untreated timber from the same period showed 90% structural degradation. 800 years versus destruction. Same tree, different treatment. Treated timber ignites at temperatures 60 to 80 degrees higher. The resin layer forms a carbonized char barrier that slows flame propagation. Synthetic fire coatings cost $40 to $120 per liter. Pine resin does the same thing for $2 a kilogram, and it grows on trees. Now, let me explain exactly why this works. Because the science is as elegant as anything modern chemistry has produced. It all comes down to one process: polymerization in place. Wood is primarily composed of 3 materials: cellulose, hemicellulose, and lignin. Cellulose gives wood its structural tensile strength. Hemicellulose provides flexibility, while lignin is the natural glue that holds the cellular matrix together. The weakness of wood is in the spaces between these components, microscopic channels and pores that allow water and oxygen to penetrate. Microorganisms penetrate and expand, breaking the structure apart. That process is called rot, and every piece of untreated wood is engaged in it. Pine resin is chemically a mixture of abiotic acid, pymeric acid, and terpene compounds. It is liquid when heated. When applied to raw wood, the resin flows deep into the pore structure. It does not sit on the surface like paint. Then it cures. The terpene compounds undergo oxidative polymerization. They absorb oxygen and link together into long molecular chains. This converts the liquid into a solid polymer network inside the wood. The wood becomes a high-performance natural composite material. The polymerized resin blocks moisture and adds compressive strength that raw wood simply does not have. Measured by the Janka hardness test, the result is dramatic. Untreated Scots pine has a hardness of approximately 1,150 newtons. After treatment, it reaches 3,200 to 4,100 newtons. That is approaching the range of some structural aluminum alloys. Moisture resistance is equally striking. Untreated pine absorbs 35% of its weight in water. Treated pine absorbs less than 4%. No water penetration means no freeze-thaw expansion, no mold, and no rot. The decay process is essentially halted. Consider the Norwegian stave churches. Some have been in service for over 800 years thanks to pine tar treatment. Treated sections showed less than 12% degradation over 8 centuries. Untreated timber from the same period showed over 90% destruction. 800 years versus effective destruction. Same tree species, different surface treatment. The fire resistance data is also revolutionary. Untreated pine ignites at 300 degrees Celsius and burns readily. Treated timber ignites 60 to 80 degrees higher. The resin forms a carbonized char barrier that slows flame propagation. Modern intumescent fire coatings cost $40 to $120 per liter. Pine resin does the same thing for $2 per kilogram. And the best part? It literally grows on trees. The future of sustainable, indestructible wood is already here. But here is what the industry did not anticipate. The knowledge survived. It just moved to the margins of the mainstream. Scandinavian countries never fully abandoned pine tar wood treatment. In Norway and Sweden, pine tar remains commercially available at hardware stores and marine supply shops. The Norwegian Directorate for Cultural Heritage recommends pine tar treatment for the maintenance of historic wooden structures. This includes the 28 surviving medieval stave churches, which are UNESCO World Heritage Sites. You can buy a liter of genuine Swedish pine tar from online retailers today for approximately $12, enough to treat 15 square meters. In 2014, researchers in Poland published a comparison study of historical pine tar treatment against modern pressure-treated CCA lumber. The study subjected matched samples of both treatments to 10-year outdoor weathering exposure in continental European climate conditions. After 10 years, pine tar-treated samples showed 8% surface degradation. CCA-treated samples showed 11% surface degradation. A 3,000-year-old folk technology outperformed the industry standard in controlled long-term exposure. The study was published in the European Journal of Wood and Wood Products. It generated no coverage in mainstream construction media. In the DIY and natural building communities, pine resin wood hardening has experienced a quiet resurgence. Online forums for timber frame builders and log cabin construction have documented hundreds of first-person applications of historical pine tar methods. These methods are used on everything from garden fencing and chicken coops to full structural timber frames. The consistent report across these communities is the same. The treated wood simply does not decay. Posts set in ground contact without concrete footings, treated with pine resin and pine tar, have been monitored for years in wet climates. They show no rot initiation. A timber framer in Vermont documented his pine resin treatment process for a post and beam barn in 2018. He treated all structural members with raw pine resin heated to 80 degrees Celsius and applied with a natural brush. His total materials cost for treating the lumber of a 1,200 square foot barn was $340. The equivalent pressure-treated lumber for the same project would have cost an additional $4,800 in materials. His barn is now in its 7th year. The treated posts show no sign of decay. An agricultural extension agent who inspected the structure in 2023 confirmed the timber integrity. Here is exactly how to do this. And it is genuinely simple enough that it becomes almost embarrassing that the industry convinced an entire civilization to forget it. Materials needed: pine resin, raw colophony or pine tar, approximately $10 to $15 per kilogram from online natural building suppliers or Scandinavian import retailers. A metal pot dedicated to resin heating, a propane camp stove, natural bristle brushes, and heat-resistant gloves. Work in a well-ventilated outdoor area. Step 1. Surface preparation. The wood surface should be clean and dry. For new lumber, this requires only basic dust removal. For existing weathered wood, wire brush any loose surface material. You do not need to sand to bare clean wood. The resin will penetrate regardless. Step 2. Resin heating. Place your pine resin in the metal pot and heat over medium flame until fully liquid, approximately 60 to 80 degrees Celsius. The liquid should be translucent amber. Do not overheat. Resin does not need to boil. Maintain heat at minimum melting temperature throughout the application process. Step 3. First coat application. Apply heated liquid resin generously to the wood surface using a natural bristle brush. Work it into the grain. Apply until the wood surface shows saturation. Allow to cool to room temperature completely. This typically takes 2 to 4 hours depending on ambient temperature. Step 4. Second and third coats. Repeat the process for 2 additional coats. 3 coats achieve a penetration depth of 3 to 5 millimeters. For ground contact or extremely wet exposure, a 4th coat is recommended. For tool handles or furniture, 2 coats provide complete protection. Step 5. Cure time. Full polymerization takes 2 to 4 weeks, accelerated by sunlight and warm conditions. The surface transitions from tacky to hard. The color darkens from amber to deep brown or near black. This is the visual confirmation that polymerization has completed. Cost breakdown: garden fence posts, $8. Deck framing, $45. Barn structural posts, $85. Camping gear, just $3. Compare those numbers to specialty wood sealants at $40 to $80 per gallon, or commercial deck coating systems costing hundreds. One important note: pine tar is slightly easier to work with than raw resin. Raw colophony offers higher hardness results, but requires more careful management. Both are widely available online, and both perform to the same fundamental standard. Start preserving your wood projects naturally today. Let me leave you with something that has stayed with me since I started researching this video. The wooden hull of the Oseberg Viking ship, excavated from a burial mound in Norway in 1904, and dated to approximately 820 AD. After nearly 1,200 years in Scandinavian soil, the pine tar treated hull planks retained over 70% of their original structural density. The ship could theoretically be relaunched with structural reinforcement. 1,200 years. Treated with $2 worth of tree resin per board foot. The average pressure-treated deck built today has a design service life of 25 years before replacement is recommended. A full deck replacement runs $15,000 to $40,000. The deck industry generates this replacement cycle reliably every 25 years. The industry chose a treatment standard that is a good product, but not the best. The best product grows in the forest. What the lumber industry understood in 1938 was not that pine resin treatment was inferior. They understood it was free and renewable. Pine resin was scalable to any individual with $10 and an afternoon, and completely outside their control. An industry cannot be built on a material that anyone can harvest from any pine tree in any forest in the temperate world. So they built the building codes, training systems, and cultural memory of construction around something else, and for 80 years it worked. But chemistry does not care about market strategy. A resin that polymerizes inside wood grain and creates a composite material harder than aluminum does not stop working because someone builds a factory. The knowledge was not destroyed, it was moved. It waited in Norwegian hardware stores and Polish research journals. It waited in Scandinavian church maintenance manuals and Vermont barn builder forums. It waited for someone to look. Some knowledge never truly disappears. It simply waits for someone to remember. If this video changed how you look at the fence post rotting in your yard or the deck boards cupping, subscribe and share. Every share puts a crack in the wall they spent billions building around knowledge that was never theirs to lock away. The next vault opens soon. What is inside is the one thing every builder throws away that could make their structure last for centuries.